Welcome back to Module 1, Unit 2, Lesson 3 of our study of the fundamentals of operating systems. Based on the text Operating System Concepts by Abraham Silberschatz, Greg Gagne, and Peter Galvin. Please have your study guide ready to make a few notes as we go along. So why don't we get started? These system call names can be specified in many ways depending upon the operating system design. One approach is to pass the names of the two files as part of the command, like you see here. This command copies the input file in.txt to the output file out.txt, which we just did on our Windows machine. A second approach is for the program to ask the user for the names. That's an interactive program. In an interactive system, this approach will require a sequence of system calls. First to write a prompting message on the screen, then to read from the keyboard the characters that define the two files, and so on. Your Microsoft DOS will give you a bad syntax error if you just type the word copy. On a mouse-based or icon-based systems, a menu of file names usually is displayed in a window. The user can then use the mouse to select the source name, and a window can be opened for the destination name to be specified. This sequence requires several I/O system calls. Once the two file names have been obtained, the program must open the input file and create and open the output file. Each of these operations require another system call. Possible error conditions for each system call must be handled. For example, when the program tries to open the input file, it may find that there is no file of that name, or that the file is protected against access. In other words, you don't have permission to do that. The program should output an error message, which is another sequence of system calls, and then terminate abnormally, another system call. If the input file exists, then we must create a new output file. We may find that there is already an output file with the same name. This situation may cause the program to abort, another system call. Or we may delete the existing file, another sequence call, and create a new one, yet another system call. As you can see, this could be scary if you wrote the file names in the wrong order. Another option in an interactive system is to ask the user whether or not to replace the existing file or to abort the program. This is a whole sequence of different system calls to accomplish this. When both files are set up, we enter a loop that reads from the input file, a system call, and writes to the output file, another system call. Each read and write must return status information regarding various possible error conditions. On input, the program may find that the end of the file has been reached or that there is a hardware failure in the read, such as a parity error. The write operation may encounter various errors depending upon the output device. For example, there could be no more disk space. Finally, after the entire file is copied, the program may close both files, two system calls, write a message to the console or window, more system calls, and finally terminate normally, the final system call. This system call sequence is shown in the figure below. As you can see, even simple programs make heavy use of the operating system. Frequently, systems execute thousands of system calls per second. However, most programmers never see this level of detail. Typically, application developers design programs according to an Application Programming Interface, API. The API specifies a set of functions that are available to an application programmer, including the parameters that are passed to each function and the return values the programmer can expect. Three of the most common APIs available to application programmers are the Windows API for Windows systems, POSIX API for POSIX-based systems, which include virtually all versions of Unix, Linux, and Mac OS, and the Java API for programs that run on the Java virtual machine. Programmer accesses an API via a library of code provided by the operating system. In the case of Unix and Linux, for programs written in the C language, the library is called LIBIC. Note that unless specified, the system call names used throughout this unit by the authors and I are generic examples. Each operating system has its own name for each system call. Behind the scenes, the functions that make up an API typically invoke the actual system calls on behalf of the application programmer. For example, the Windows function createProcess, which is used to create a new process, actually invokes the NT-createProcess system call in the Windows kernel. Why would an application programmer prefer programming according to an API rather than invoking system calls? There are several reasons for doing so. One benefit concerns program portability. An application programmer designing a program using an API can expect the program to compile and run on any system that supports that same API. Also, actual system calls can often be more detailed and difficult to work with than the API available to the application programmer. In fact, many of the POSIX and Windows APIs are similar to the native system calls provided by the Unix, Linux, and Windows operating systems. Another important factor in handling system calls is the runtime environment. Runtime environment refers to a full suite of software needed to execute applications written in a given programming language, including its compilers or interpreters, as well as other software such as libraries and loaders. The system call interface intercepts function calls in the API and invokes the necessary system calls within the operating system. The caller doesn't need to know anything about how the system call is implemented or what it does during execution. Rather, the caller need only to obey the API and understand what the operating system will do because of the execution of that system call. Therefore, most of the details of the operating system interface are hidden from the programmer by the API and are managed by the runtime environment. The relationship among the API, the system call interface, and the operating system is shown in this figure, which illustrates how the operating system handles a user application invoking the open system call like this one. System calls occur in different ways, depending upon the computer in use. Often more information is required than simply the identity of the desired system call. The exact type and amount of information vary according to the particular operating system and the call. For example, to get input, we may need to specify the file or device to use as the source, as well as the address and the length of the memory buffer into which the input should be read. Of course, the device or file and the length may be implicit in the call. Several general methods are used to pass parameters to the operating system. The simplest approach is to pass the parameters in registers. In some cases, however, there may be more parameters than registers. In these cases, the parameters are generally stored in a block or table in memory, and the address of the block is passed as a parameter in a register as shown in the next slide. Linux uses a combination of these approaches. If there are 5 or fewer parameters, registers are used. If there are more than 5 parameters, the block method is used. Parameters also can be placed, or pushed if you recall, onto a stack by the program and popped off the stack by the operating system. Some operating systems prefer the block or stack method because these approaches do not limit the number or length of parameters being passed. Here's that image of the parameters being passed. System calls can be grouped roughly into 6 major categories. Process control, like the one you're seeing on this screen. File management, device management, information maintenance, communications, and protections. Let's look at the types of system calls that may be provided by an operating system. As I've already mentioned, we normally refer to the system calls by generic names. Throughout the text, however, the authors provide examples of the actual counterparts to the system calls for Unix, Linux, and Windows systems. Since we've been bombarded by so many system calls in this one short lesson, why don't we take a break before we actually start exploring the different types of system calls in detail? Look over your notes, take a look at some of those APIs that we were just describing, take care of any business that you might have, and when you're ready, come on back and we'll start lesson 4.